Okay, we're back at it. Today we're going to look at an interesting kind of inequality. It's known as a compound inequality. It's Chapter 2, Section 9. Now, before we get started, let's talk about what a compound inequality is. And I'll give it to you kind of as an example. We have child safety seat laws in California in a car, where if a child is below a certain weight or below a certain height, they have to be in a car seat, right? Well, that's a compound inequality because you have to meet two conditions if you want to get out of that car seat. You have to be over a certain weight and you have to be taller than a certain amount. So that's what a compound inequality is. It's where you have to meet one or both of two conditions. Now, what we're going to do is look at that mathematically, and it's called compound inequalities. So, they come in different types. The first type we're going to talk about is the AND statement, where the number or numbers in your solution have to meet both of the conditions that we've got here. So I've got two conditions. X is greater than or equal to -5 and x is less than or equal to 7. So we want to find all the numbers that meet both of those, because it's an AND statement, both of those conditions. And I want to do this graphically just to kind of help you out a little bit. So we're going to start with the statement x is greater than or equal to -5. Well, if I were to graph that separately, it would look something like this. Okay? Here is -5, and these are all the numbers that are x are greater than or equal to -5, right? All these numbers. Then we've got the other condition, which is x is less than or equal to -7. So that would be all these numbers, where this is -7, and these are all the numbers that are less than or equal to -7, okay? Now, what we're going to do is we're going to combine those two graphs onto one number line. So we're just going to bring both of these down, and we're going to be looking for where they overlap, because it's where these two graphs overlap that we are meeting both of the conditions at the same time. So we'll bring this one down, solid circle there, okay? And we'll bring this one down, solid circle there, and it's where we have two graphs right in here. That is the area where the numbers meet both of the conditions. They are greater than -5 and they are less than 7. So that's how a compound inequality works. Now let's take a look at an example type of problem you might see when you're doing these. Okay, so this is example forest, and it says solve and, I'm going to go back up here. I forgot to show you something. We have this compound statement, which is x is greater than or equal to -5. Another way to write that is just to flip this whole thing around. So I've got -5 is less than or equal to x. These two are equivalent to each other. The other statement I had was x is less than or equal to -7. Now what I'm going to do is I'm just going to marry these two statements together. I see these two x's. Why write two x's when I can just write -5 less than or equal to x is less than or equal to -7. That's how we write this compound. Okay, and I don't know why that's a negative. That should be plus. Sorry about that. So that's how you can write a compound inequality AND statement. You can just marry the two statements together and write it like that. So I had to go back to that because here you see this, where the two statements have been married together. You've got -4 is less than x minus 4, and you also have x, let me start again, -4 is less than x minus 5, and you also have x minus 5 is less than or equal to -1. And we want to solve and graph this. Well, when we were doing equations, we talked about there being a left side and a right side of the equal sign. Well, here we have two statements, inequalities. We have three sides. We have the left, the middle, and the right. So anything we do, we have to do to all three. So what I'm going to do is I want to get x by itself, so I have to get rid of this minus 5. So I'm going to add 5 to the middle, going to add 5 to the right, and I'm going to add 5 to the left. So see how I had to do that in all three places? All right, the negative 5's cancel, and I have negative 4 plus 5 is 1, is less than x is less than or equal to 4, because negative 1 plus 5 is 4. Now, that's what I want. I just have to graph it. So I draw my number line. I'll say that 4 is here, and I'll say that 1 is here. This gets an unfilled in circle. This one, because it's or equal to, gets filled in, and it's every number in between, okay? So that's what the graph would look like as a solution to this. Every number in the shaded area is both greater than negative 1 and less than or equal to 4. Let's take a stab at another one. Okay, this is example Mr. B. So I want to isolate the x, so I'm going to subtract 7 from all three sides. And this becomes negative 9 is less than negative 3x is less than negative 3. Now, I'm already thinking ahead because I see that negative 3. When I divide by negative 3, I have to change the direction of both of the inequality symbols. So we're going to divide everything by negative 3. And I get 3 is greater than x is greater than 1. Notice how everything switched on the inequalities. Now, what I like to do, you don't have to do this, but what I like to do is put this so that the two numbers are in order from left to right. So I would rewrite this as x is less than, 1 is less than x is less than 3. So I just took this whole statement and flipped it. This is equivalent to that. And then we just have to graph it. Here's 1, open circle. Here's 3, open circle. And it's everything in between. So everything in the shaded area meets both of those conditions. So those are your examples on and compound inequalities. But there's another kind as well, and that's known as or statements. So when we did and, the numbers had to meet two conditions at the same time. But when we do or, it only has to meet one condition at a time. It can be less than 5 or greater than 4. It can be, so it only has to meet one of those conditions, and that's what an or statement means. So let's look at this a little bit. We've got x is less than 3 or x is greater than 7. So let's think about what that means. We'll break up the graphs again. So here's a graph of x is less than 3. All right, so any number in this area is going to be less than 3. Then we have this condition, and we'll graph that here. Anything on this arrow, anything on this number line is greater than 7. We're going to bring those down, but now this time we're not looking for overlap. What we're looking for, we're just bringing everything down. We don't have to look for overlap in the two graphs because we only have to meet one condition or the other. We don't have to meet both. So we bring this down and we bring this down, and our combined graph looks like this. Anything in the magenta area meets this because it only has to meet one of those conditions, not both. Now I do have to tell you something here. Where we did the and statements, we were able to combine them into a single statement. We took that one, and we combined them into a single statement. We don't do that with or statements. So you wouldn't write negative 3 is greater than x is greater than 7. We don't do that. So I'm going to put a line through that and say don't do this. Okay? You just don't see it. So let's look at some examples. Mr. Hodap is my example here, and it says solve and graph. We have two conditions. 4x plus 3 is less than negative 5, or negative 2x plus 7 is less than 1. So let's solve both of those. We're going to subtract 3 from both sides here. Those cancel, the 3's cancel. So we have 4x is less than negative 8. Divide by 4. Now let's make a note here. I'm dividing by 4. 4 is a positive number. Now I'm dividing 4 into a negative, but that doesn't matter. It's what I'm dividing by. So this doesn't generate a change in the inequality symbol. So the 4's cancel, and I have x by itself. X is less than negative 2. Or, and I'll come over here and solve this one. Subtract 7 from both sides. The 7's cancel because 1 is negative and 1's positive. Bring down the negative 2x is less than negative 6. Now I go to divide. This time I am dividing by a negative number. So when I divide by negative 2, the negatives 2 cancel. I have x is greater than 3. Note I had to change the inequality. And if we go to graph this, we'll put negative 2 here, open circle, shade to the left. We'll put 3 here, open circle, shade to the right. Any number in these two areas will meet one of these conditions, and that's all we have to meet. We just have, because it's an or statement. So it can be here or there. All right? Last one, Mr. Russell. Now this one's interesting. And you'll see why when we go to graph it. Again, it's an or statement. We're going to solve these independently. I have x plus 2 is less than 7, so I'm going to subtract 2 from both sides. The 2's cancel because one's positive and one's negative. So I have x is less than 5. Or, and over on this side, I'm going to add 1 to both sides. The 1's cancel because one's negative, one's positive, and I have x is greater than negative 3. Let's put our number line down. And let's graph this. So let's do the 5. Here's 5. I get an open circle. And anything less than that meets the first condition. So this is x is less than 5. Now we'll put down the x is greater than negative 3. Negative 3 goes somewhere over here, circle, and any number greater than that. Well, look at the line. Everything on my number line has been shaded. And because it's an or statement, we only have to meet one of the two conditions. Every number on the number line meets one of the conditions. So my solution here is actually any real number. Every number meets one of these two conditions. So my solution is any real number. And I can write these so that we have overlap and any real number works. I could also write it so that no number works. So you're going to want to look out for those. So this is a lesson on compound inequalities. We took a look at and statements, okay, how they overlap. And in an and statement, you have to meet both conditions. So you have this kind of a graph. And then we looked at or statements, where you only have to meet one of the conditions. So generally, you